start class. So spring break's officially over now. I have, as usual here on the screen for you, I have posted the, just the homework list, right? And so the thing that's really to key in on is this first homework about basic differentiation rules, which we talked about before the break, right? So these are the shortcut rules that allow us to differentiate functions, without having to go through that clumsy limit process, right? And so these are great time-saving devices. And so we have a lot more of those to learn today and also next time. So it's going to be kind of the next couple of days are going to be kind of technical because we're going to be just going through these rules, and so we'll be doing lots of differentiation of different functions, right? Just over and over again, just so that we can practice all these rules because they really are beneficial to us to prevent us from having to, compute right. So this one, it was originally due on Tuesday today, but I put it back till tomorrow. So it's due tomorrow at midnight. So I'd like to keep that one. And these assignments have quite a few problems on them. Each problem itself is not really maybe all that bad. Some of the problems are probably difficult, but most of them are probably pretty straightforward. But there are a lot of them. So because you have to have a lot of practice with these rules so that you can memorize them and be able to use them really quickly when you need them. Because in calculus, you're going to be differentiating functions all the time. And so you need to be able to do that confidently and quickly so that you can, approach more difficult problems, right? And not get hung up on the more rote things. So anyway, this one's due tomorrow. And then I've got the next one set for Saturday, and so we're going to talk about this one today. So I don't know. We'll think again on Thursday if Saturday's a good due date. This one on the chain rule, I don't think is going to be due on Saturday, but I've just got it set there on Saturday, so it's not, due next time, right? So we'll talk about adjusting that one on Thursday. Okay, so that's kind of where we are with the homework. So notice that there is this, I don't know why this, I was wondering why that asterisk was there. So you have a class participation grade, right, that's part of your grade. So this was in the syllabus, and I'm going to assign such a grade after every test. And so usually that's based on if you've been, responding to my questions in class, right? So and so it's easy to make a really high score. But if you haven't been coming to class and I haven't been able to ask you a question, then that's when things get a little bit trickier. So that's why, for instance, Avery, I was going to ask you this question so I can make sure to check you off and you can get a good score on that first class participation grade. I think this one is set to be due tonight. So but you don't do anything this. I'm the one that assigns the grade. And so it will show up in the grade book, I guess, after midnight. So for most of you, this is going to be 100, right? So so you'll see that in your grade book when you in my grade when you look at that, after midnight tonight. Okay, all right. So that's where we are with the homeworks. Y'all have any burning questions that you need to ask me at the moment? So that can include homework questions.
Yeah, can I please ask you a question about 2.2?
About which one?
2.2, yeah, that.
This one? Okay.
Number 11.
Yeah, let me open it. So maybe this is, I think we've talked about all these things. I was going to say maybe this is something that we haven't talked about yet, but I think all of these things we've talked about, maybe not at length. Oh, this one?
Yeah.
Okay. So so that one is that one's pretty straightforward, although it looks hard. It's not as hard as it appears, but maybe the answer is the issue there, Donna. Were you not able to start it, or you thought you had the answer and it didn't? WebAssign wasn't grading it right, or something like that?
So I started it using the power rule.
Yeah, that's exactly correct.
Yeah, and then you take the constant out, but then after that, I was just kind of lost.
Oh, okay, all right. So do you have in front of you your version of the problem, just so that we can be working on exactly what you're, because mine's going to be slightly different.
Okay, I can just one second. I can pull it out real quick.
Well, that's okay. We'll just look at this version and then you can see the, and you'll be able to, I think the only thing that will be different is these numbers. So that's not going to make that much difference to the problem. Okay, so let me switch over here so I can have a place to write. And see if I can scroll down to, if I have any blank paper here. Oh, great. Okay, so here's some blank paper. All right, so there's the, so the function is f of t is, at least my version of the problem is 2 t to the 2/3 power minus 7 t to the 1/3 power and then plus 8. Okay, and so all we want to do is calculate the derivative. And what Donna said was exactly correct. We just want to apply the power rule going term by term through this expression. So remember, terms are quantities that are added or subtracted. And one of the really nice things about differentiation is that you can, when you have an expression where you have lots of terms, things that are added and subtracted from each other, like in this expression, you can just go term by term and differentiate each of the terms individually. So you don't have to think of the whole expression at once. You can just think of one term at a time. So we can differentiate this by first differentiating the 2t to the 2/3 and then differentiate the minus 7t to the 1/3 and then differentiating the 8. But that 8, let me do that first, actually, a little bit out of order. That is easy to differentiate. 8 is easy to differentiate because that is a constant. So, and remember, constants, their derivative is 0. Remember, a constant is just a plain number. So, and the derivative of a plain number is just 0. This is not a constant, however, because the second term is not a constant because it has a variable, right? However, now, so let's do these two terms. But these two terms we can differentiate because we can use the power rule, because here we just have our variable raised to a power. And so the power rule says all you have to do is, remember, you want to bring down the power, right? So I would have 2/3 times, keeps the 2, it keeps the constant, and then t to the, and then remember you subtract 1 from the exponent. So that would be 2/3 minus 1. And then same thing in the second term, because this is also just a power of t. So you bring down the 1/3. It's going to multiply by the 7, but just keep the 7, and then t to the 1/3 minus 1. Right? Subtract 1 from the exponent. So we get, let's see, 2/3 times 2, I guess that's 4/3. So I have 4/3 t to the minus 1/3 power, and then this is minus 7/3 t to the minus 2/3 power, and then the plus 0 I'm just going to drop. So really, this is already the derivative. So you can really use that and evaluate that, even with the negative exponents. But normally we might simplify this a little bit and get rid of at least the negative exponents. And remember, you can get rid of negative exponents by taking the reciprocal. T to the minus 1/3 power means 1 over t to the positive 1/3 power. And don't do anything with the 4/3 though. And then minus 7/3 times, and t to the minus 2/3 power means 1 over t to the positive 2/3 power. So now let's see, let's multiply the 4/3 times the 1 over t to the 1/3 power. So that's 4 times 1, multiply the numerators, right, over 3t to the 1/3 power. And then minus the second term is 7 times 1, which is 7 over 3t to the 2/3 power. Now, I would probably, you could maybe stop here. Maybe WebAssign would grade this correctly already, or you could stop here. and the reason that I would quit I would probably go to this level, but this might also be okay. Because this looks very similar to the original expression, right? Okay, in the format of it, we just have t raised to a power in both in both the original formula and then in the formula for the derivative. So I always like to make the formula for my derivative look like the way the original function was written. It's not going to be the same function, of course, but I want it to look like the original function was originally written. So I think either this one would probably be acceptable by WebAssign or on a test. This one would be acceptable by WebAssign or on a test. Now, the reason I say stop at this point is you could simplify this, rewrite this further. But if you remember what 1/3 power means, remember 1/3 power is the same as cube root. So you could rewrite this as 4/3 times the cube root of t. And then minus 7/3, and then t to the 2/3 power is cube root again. The thirds here means that you're going to have cube root, and then the 2 stays as an exponent. So t to the 2/3 power means the cube root of t squared. So you could make the answer look like this, and it's the same. In some cases, this would be better, but I didn't rewrite the fractional exponents as radicals here because they weren't written as radicals in the original formula. Donna, does that make sense? Why I stopped without doing this?
Yeah.
I was just trying to make it look like the original problem was written, but you could have written the answer like this. It means the same thing. Okay, well. All right, so you can try this one, you can try this one, or you can even try this one and see which one WebAssign accepts as the answer.
That's weird. I was doing the same thing with the problem they gave us, like the same exact steps, but I don't know. I just couldn't get the answer correct on WebAssign. But it's cool. I can figure it out.
Okay. All right. Well, you can if it doesn't work, then you can email me that problem, and I can take a look at and maybe figure out what WebAssign is really expecting. Do y'all have other questions on? Anyone have other questions on this homework while we're talking about it since it's due tomorrow? Yeah, go ahead.
Can we do question 16?
16. Oh, just the one that I'm looking at here. Wow. Okay, so so this one is an applied problem, right? So we're going to have to use our skills here to to answer some more practical questions. Okay, let's see if we can. Wow, this is a lengthy one, so let's see if we can figure out all these answers. All right, so a silver dollar. So this sounds like a problem that we've done, right? Except because we dropped a screwdriver one time off of a building, right? But here we're dropping a silver dollar from the top of a building that's 1,312 feet tall. And then it says use this position function for a free falling object. So this function applies to any object that's falling from a height if you ignore wind resistance. So I don't know how aerodynamic a silver dollar is, but we're going to ignore. We're going to pretend that it's not very aerodynamic. So the air resistance is not going to make much difference. And so then we can use this particular formula. This what you have to know about this formula. So Daniel, maybe this is where you got messed up there. You have to know what the V sub 0 means because you have to fill in that value, and you have to know what the S sub 0 means because you have to fill in this value as well to actually use this function. And I think the S sub 0 is the initial height. That's the initial height of this object, which is 1,312 feet, right? Because you're dropping it off of this building. Okay, so that's easy to fill in. And then the V sub 0 is the initial velocity. So how fast is this thing going initially? How fast is it going initially, Daniel?
It's going to be 32 feet per second.
And not initially, because when you drop it, right, when you release it, how fast is it going when you first release it? You got it there and you drop it. How fast is it originally dropping?
0.
0, right? Yeah. So yeah, because it doesn't have any speed, right? When you first release it, of course, it's going to pick up speed really rapidly because of gravity, right? But initially, it's 0. See, you're not throwing the object, right? So you're not giving it any sort of initial velocity. You're just releasing it. So you're right. It's 0. So that's nice. That this coefficient v sub 0 is 0. So you can so this middle term just disappears. So you can fill that in, and you can fill in the 1312, right? So let's do that, and that gives us our what's called the position function. And now I think we can answer all of the questions based on that position function. So let me go back over here and let's fill in the correct position function. So the correct position function is S of t. Sorry, my parentheses there looks, not sure what it looks like there. But so S of t is equal to, so it was minus 16 t squared, and then, plus 0 times t, right? Because your initial velocity is 0, and then plus the initial height, which was 1312. So of course, this middle term, you can just forget about the middle term, right? And so you really have just the minus 16 t squared plus 1312. All right, let's see now what they're asking us. Determine the position and the velocity functions for the coin. Well, we wrote in the position function, right? So Daniel, what would the velocity function be? So velocity speed, that's a rate of change. So what are they really referring to here when they ask you for the velocity function?
The speed of the how far it's dropping.
Yeah,
how
they
fast
want
it's
a
dropping.
function that will give you the speed, or the function, right? They want a function, a formula that will give you the speed, or a formula that will give you the derivative. What function would that be in calculus? What function would that be? What function tells us the rate of change of something?
The velocity.
Yeah, that's what we're going to fill in, the velocity. Yeah, okay, so that's what they're asking us for. But what do we know the velocity as, or the velocity function as? They're calling it velocity because this is a physics problem. But in our math class, what do we call this function? Begins with a D, Daniel.
Derivatives.
Derivative, right? Yeah, the velocity is the derivative, right? Okay, the velocity is a rate of change, right? It's how fast this coin is, in this case, dropping. So that is the same as the derivative. Okay, so when they're asking for the velocity, they're really asking us in a roundabout way, in the physics way, for velocity. So all we have to do, Daniel, is be able to differentiate this function. What is the derivative of this function?
It's 32.
Yeah, minus. The minus is important, right? Because this thing is dropping. So it's minus 32t. And again, you can get that from the power rule, right? Bring the 2 down, multiply it by the minus 16. That gives you minus 32. Subtract 1 from the exponent. So you get 2 minus 1, which is just 1. So you get minus 32t. And then the constant, its derivative is 0. So you get a very simple velocity function here, just minus 32t. Okay, so probably we didn't stress this enough, in class before this homework. But first derivative in calculus, in physics, that is usually interpreted as velocity. Okay, all right, and it can be negative. It doesn't have to be positive. We often think of velocities as always being positive, but actually they can have negative values. All right, now let's go and all right, let's go and see if we can figure out how to answer the rest of the questions. Now, the part B here is a little bit is easier than it appears, because it says what is the average velocity on the interval from 3 to 4? That means from the 3rd second to the 4th second. Okay, you don't need the velocity function to answer this question, Daniel. this means the average rate of change, okay? So what was the average rate of change from second 3 to second 4, all right? Okay, so this is an average rate of change problem. So we just use our average rate of change formula to calculate this, all right? So so it would be average, see, what is that average rate of change calculation here going to be, right? Remember, we're going from the 3rd second to the 4th second, right? So it would be S of 4 minus S of 3, right? Okay, because you're going from t equals 3 to t equals 4 over, and then we get a very easy number in the bottom there, just 4 minus 3. So if you can calculate S of 4 using this formula, right, and then also calculate S of 3 using this formula, and then just plug that into your average rate of change quotient, and you can figure out what this average velocity is. I'm not gonna actually calculate this, but you can fill them in pretty easily and do this arithmetic, right? Now, on the other hand, when you calculate the average velocity, that is what's happening on average from the 3rd second to the 4th second. But remember, the coin is constantly speeding up, right? So the velocity after 3 seconds is less than the velocity after 4 seconds, okay? But this question just says, what was it on average from the 3rd second to the 4th second? But the next question, part C, is going to be more specific. It says, find the instantaneous velocity. Exactly how fast was the coin traveling after 3 seconds? And exactly how fast was it traveling after 4 seconds? So in other words, as I said before, right, it's kind of a colorful illustration of this. If you had a speedometer on the coin, right, what would the speedometer read after 3 seconds? And then what would the speedometer read after 4 seconds? And there you can just use your velocity function, okay? So you don't have to compute an average rate of change, just use the velocity function, calculate v of 3, and then also calculate v of 4. That's what they ask you for, right? Let's see, what is v of 3? That's minus 32 times 3, so that's easy enough. That's minus 96, and it's feet per second, okay? Feet per second. So the coin is dropping 96 feet per second after 3 seconds. But after 4 seconds, it's going to be dropping faster, right? Because that's just how falling objects work, right? And so now plug 4 into your velocity function, and you get, minus 32 times 4. What's that? Minus 128, right?
Yeah.
So
right.
after 4 seconds, it's dropping at, after 4 seconds, of course, it's going faster, right? So after 4 seconds, it's dropping minus 128 feet per second, okay? So keep in mind this difference between instantaneous velocity, what's happening at a particular second, and then versus average velocity, which is a different sort of question. Let's see, what's the last part here? Well, this is easy, right? How long does it take for the coin to reach the ground? Eventually, it's going to hit the ground, right? It's falling from 1,312 feet. Eventually, it's going to hit the ground. How do you answer that question, Daniel? So how do you figure out when it hits the ground? What process do you go through to answer that? See, this is the formula that gives you that's the formula that gives you the position. So that's the formula that gives you the height after a certain number of seconds. So see, what you're interested in knowing is when the height is what? When it hits the ground, what's the height?
0.
0.
0. So you would take your position function, not your velocity, but your position, right? This tells you how high it is, and you would set that to 0 and try to solve that equation. So you would have minus 16 t squared plus 1,312 equal to 0. and try to solve that equation. Well, that should be pretty easy to solve. Maybe a calculator to help you with that, but just solve that equation. Let's see, let's do that. Let me bring the minus 16t squared back over to the left. So I would have positive 16t squared is equal to 1312. Divide both sides by 16. So I have t squared is equal to 1312 divided by 16. I have no idea what that is, but I don't know if that comes out to be a whole number or not. So t squared is 1300 divided by 16, and then just take the square root of both sides. So you get t is equal to the square root of 1312 divided by 16. That may turn out to be a reasonable number, or it may have to just write down a decimal approximation for that. Let's do that on the calculator. So let me do that really quickly here. 1312 divided by 16. Oh, that's nice. That's 82. And then we just take the square root of that, which is going to be a little bit more than 9, I think, right? So, so this turns out to be approximately 9.06. It's really 9.055 with a bunch of other decimal places, but approximately 9.06. So that's how long it takes to hit the ground. Just a little bit more than 9 seconds. Now, the final question was, how fast is it going when it hits the ground? Okay, so it's probably going pretty fast, right, when it hits the ground. So how do we answer that one? Well, there's the time it takes to hit the ground. So you simply take that and plug that into your velocity formula, right? Okay, so take the 9.06 and plug that into the velocity formula, and that will tell you the velocity after 9.06 seconds, which is when it hits the ground. So so we just calculate b of 9.06. So that is minus the 32, right, times 9.06. So whatever that turns out to be, something like 300, I don't know, something like that, right? Minus 300. That's how fast it's going when it hits the ground. Ooh, wow, that's a multi-part problem, but that's a good problem because it involves lots of different concepts in it. Okay, is that the last problem? So is that the hardest problem? Close to it. Okay, all right. So hopefully that's almost the hardest problem. Did you get all that, Daniel?
Yeah, I get it now.
Does everyone understand?
Most of
Everyone
it,
sort
I
of
just
understands that example?
Yeah.
Okay. All right. Well, all right. So, all right. So let's go on to the notes now before we get too behind. Okay. So if you have other homework questions, you can, you can email them to me through Ask Your Teacher, or how come I don't see that? Because I'm the teacher. Oh, is it over here? It may be blocked from me. All right. So you can do it through Ask Your Teacher, Ask Your Instructor, or as always, right, you can visit Madison, during her SI hour, right? And you can also ask these same questions. All right, I'm going to switch back to the notes here. And so let me scroll back up to where we really want to be in the notes. And that's not too far up because we were almost through with these notes. Remember, the last rules that we learned last time, the last differentiation rules we learned right before the break were rules for differentiating the sine and cosine. And those turn out to be really convenient and easy to remember. So if you're trying to differentiate the sine function, this trig function, that's a function and it has a derivative, and it turns out its derivative is just the cosine. So the derivative of sine of x is cosine of x. So a really easy derivative to remember. So that's one that you'll find really easy to remember. Derivative of sine is cosine. And the reverse is almost the same. The derivative of the cosine is the sine, except it's negative. So the derivative of the cosine is minus the sine of x. So please keep in mind that minus sign, okay? Derivative of cosine is minus the sine of x, right? But otherwise, those are very easy functions to differentiate because their derivatives are other trig functions, right, that are easy to remember. Let's try one just to start things off again with just to do a little recall practice here to start with. So let's look at this function s, which is just cosine of t minus pi over 3 times the sine of t. So that's a pretty typical trigonometric type function, right? And let's see if we can find its derivative. So you could write that down as ds over dt, right? Because those are the variables that are being used in the problem. So ds over dt means the derivative, or you could also write this down in the more modern notation as s prime, or you could write s prime of t, since the input variable is t. These things, these two expressions mean the same thing. All right. So see if you can differentiate that, keeping in mind, right, what we just mentioned about what the derivative of the cosine is and what the derivative of the sine is, right? Okay, so Avery, I'm going to ask you this one when we get together. So everyone take a couple of minutes to try to differentiate that, right? Okay, but it's really easy just because of these are easy functions to differentiate. Okay, so were you able to get something sort of written down there for that? All right. So Avery, let me ask you. You can type it in too, as best you can on the chat. What is the derivative there of s? Remember, we can take it term by term, Avery. So you can just start with derivative of cosine of t first, and then move on to the derivative of minus pi over 3 times sine of t second. Right? That's what the differentiation rules allow you to do. So what is first there, Avi? What's the derivative of cosine of t that we just mentioned? Are you there? I can't hear you, but you can type it in. What's the derivative of cosine of t? That's right. Minus sine of t. Perfect. Okay. So see, you got the half of it there already correct. Derivative of cosine of t is minus sine of t. And so that's the first part. Now let's take the derivative of the second term here. And the pi over 3 is just a constant. So don't let that fool you, okay? Or don't let that make you think this is more complicated than it is, okay? Pi is just a number, so it's just a constant. Of course, 3 is just a number, right? It's just a constant. So pi over 3 is just a constant. So that you're just going to keep as part of the derivative, that constant. And all you really have to differentiate here is sine of t. So, but that's easy, right? What's the derivative of sine of t? Avery, what's the derivative of sine of t? That's every calculus student's favorite question. What's the derivative of sine of t? Because it's so, or sine of x, because it's so easy to remember. Can you type it in there for me? Is it A? Not sure what A is, because there's no A here. It's almost what you said, maybe just typed wrong there. All right. So you told me the derivative of cosine is minus the sine, right? Okay. So almost as easy or easier is the derivative of sine. The derivative of sine is, what's the derivative of sine going to be? Right. Okay. It's cosine. So altogether here, you would have minus pi over 3 times cosine of, don't forget the t though. Okay. You have to have the t in there. So there it is. It's just that easy. Just minus sine of t minus pi over 3 times cosine of t. Okay. So very easy formula. Maybe not an easy function to graph, okay, but it's very easy to take the derivative of this function using our differentiation rules. So that's the whole point of the differentiation rules, is they really help us very quickly find derivatives, right, without having to go through too much additional work. Now, let's learn now some more advanced differentiation rules, though, okay? Because for functions that are maybe a little bit more complicated than the ones that we saw in these prior notes. All right, so look at these two functions, f of x here, which is 3x squared times sine of x, or even a little bit. See, that's a little bit more complicated function than the ones that we had in these notes that we just finished. Or this one is especially more complicated, right? G of x is 5x minus 2 over x squared plus 1. Okay, so it turns out that the very basic differentiation rules that we just went through in the prior notes, those are not quite powerful enough to allow us to differentiate a function like this one or a function like this one. Okay, so we're going to learn today just some little bit more advanced rules that will help us handle a little bit more complicated formulas like these. All right, and the first rule that we're going to learn is what's called the product rule, and then we'll learn a complementary rule called the quotient rule. And as you'll see, we'll be able to use the product rule and the quotient rules to help us differentiate functions like this one, f 3x squared times sine of x, or functions like this one, 5x minus 2 over x squared plus 1. Okay. All right. So let me show you the product rule first. And when you see the product rule written down in correct mathematical terminology, it looks like it's confusing, but it's really not once you understand the structure of the product rule. All right. So what the product rule says is, if you have a function and you can think of it as the product of two simpler functions, okay? So if you have that situation where you have some function's formula and you can think of it as that formula as being the product of two simpler functions, then the product rule shows you how to differentiate such a function. What I like to think of, how I like to think of the product rule is, if I have a function whose formula is the product is the key here, the multiplication of two expressions, right? Some expression times a second, first expression times a second expression, then the product rule can apply in helping you find the derivative, okay? This exp1 here is my shorthand for expression 1. The exp2 is my shorthand for expression 2, all right? So if you have a function whose formula is the product of one expression times the second expression, then the product rule is a great simple way to help you find the derivative. All right, now what is the product rule? Okay, right. How does it actually work? All right. So what the product rule says is, well, here's how you find the derivative of such a product. Okay. What you do is you take the derivative of the first expression, times the second expression, but don't take the derivative of the second expression. Then you alternate. You keep the first expression, and then you multiply it times the derivative of the second, okay? So it's this alternating pattern, derivative of first factor times the second factor, plus the first factor times the derivative of the second factor. Remember, the product rule applies when you have a product, okay? So if you don't have a product, you're not going to use the product rule. All right, now, okay, there it is expressed in mathematical language, but let's actually apply it in practice, and you'll see how easy it is to use. Okay, so I'm going to come up and talk about the quotient rule later. Let's first try the product rule. So let's try it actually on that example that I just gave you a moment ago, right? We have this function h of x, and it's 3x squared times the sine of x. Okay, so notice that this, here's the key thing you want to notice here. Notice that this function's formula is the product of two simpler expressions, right? You can break that up in different ways, but probably the most obvious way to break this up is here's one expression, 3x squared, multiplied by this second expression. So see, the formula for h is the product, right? It's the multiplication of two simpler formulas or two simpler expressions. And again, whenever you have a situation like that, then you can find the derivative, if that's what you're trying to do, by using this so-called product rule. So here's what the product rule tells us will be the derivative of this function, okay? The product rule says, okay, take the derivative of the first expression. So take the derivative of the 3x squared. What is the derivative of 3x squared, by the way? That should be pretty easy to compute. What's the derivative of 3x squared?
6x.
6x, exactly, right? So the derivative of 3x squared is 6x. That's just the power rule, right? You bring down the 2 times the 3 and then subtract 1 from the exponent. So you get 6x to the first power, or 6x, right? So you take the derivative of the 3x squared, and then you multiply it times the sine of x, but don't take the derivative of sine of x, okay? Just keep sine of x first, all right? Then you alternate that. Keep the 3x squared, and then multiply it. Then take the derivative of sine of x. But what's the derivative of sine of x? As we just learned a moment ago, what's the derivative of sine of x? Yeah, Zachary, that's right. It's cosine, right? So derivative of sine of x is cosine of x, okay? There it is. There is your derivative function. It's just 6x sine of x plus 3x squared cosine of x, right? See how easy that was? Now, let me caution you about the mistake that you do not want to make, okay? You don't want to oversimplify the product rule. So students that haven't been doing their homework or haven't been paying attention, when I ask them to differentiate a function like this one, right, here's what they'll say. They'll think, okay, I take the derivative of the 3x squared, that's 6x, and then I take the derivative of the sine of x, that's cosine of x. So they write down the answer is 6x times cosine of x, okay, right? They just take the derivative of the first one, derivative of the second one, multiply them together, okay? So this is not the right answer, all right? So this is not what you want to write down as the answer. The answer is kind of like this, but but it's more complicated, right? You have to go through this alternating process. So it is a derivative of 3x squared, but then keep the sine of x plus, then keep the 3x squared and take the derivative of cosine of x. Let's try another one using the, let's try another one here using the product rule, okay? So let's look at this one. So 2x times cosine of x minus 2 sine of x, and all I want to do is find the derivative here. Now, really, we're going to combine several rules in finding the derivative of this formula. First, remember, you can go term by term in finding the derivative. So you can start first by finding the derivative of the 2x times the cosine of x, and then you can move on to finding the derivative of 2 times sine of x, okay? Because these are quantities that are, in this case, subtracted. Remember, if you have quantities that are added or subtracted from one another, when you find the derivative, you can just go one quantity at a time, right? So let's start by first finding the derivative of 2x times cosine of x. And notice that is a product, right? Because you have this quantity, this expression 2x times this expression cosine of x. Those two are multiplied together to form this term. So we will use the product rule here. We will first take the derivative of 2x. What's the derivative of 2x? Someone can say it in or type it in for me. What's the derivative of just 2x?
2.
2, right. So first you get 2, and then keep the cosine of x, right? Then plus, now keep the 2x, and then take the derivative of cosine of x. But what's the derivative of cosine of x?
Sine.
Minus the sine, right, okay? So the derivative of cosine of x is minus the sine of x. So all of this is the derivative of 2x cosine of x. Now you just move on to the second term. Now you want to find the derivative of minus 2 times sine of x. Now, this also is a product, okay, because you have the 2 times the sine of x, but you don't have to use the product rule here, okay? So you don't have to make this into a product rule problem, because this first factor that's multiplied times the sine of x, that is just the constant 2. So when you're just multiplying a constant times something, the derivative is easier. Just keep the 2 and then take the derivative of the sine of x, right? You understand the difference between these two terms? This one is easier than this one because this is 2x cosine of x. So see, this 2x has an x in it. This is just 2 times sine of x. The 2 is just a constant. So when you're multiplying by a constant, the derivative is easy. Just keep the constant, minus 2, and then take the derivative of sine of x. What's the derivative of sine of x? As we've now said 5 times today. What's the derivative of sine of x? Zachary, you get, yeah, cosine of x, right. So the second term is easy to differentiate. You just get 2 times cosine of x. So altogether here, what do we have? We have, these two cancel, right? So I have 2 cosine of x minus 2 cosine of x. So those cancel, and you just get left with the middle term. So you just have minus, I'm going to put the minus in front. So I have minus 2x sine of x. That minus sign I'm going to write in front of the minus 2. So that's it. There's your, there is the derivative. All right, now, before we try even more examples, let's go back and let's mention the second rule, which is called the quotient rule. So this, again, is just a companion to the product rule. And this helps you when you have a function whose formula is the quotient, the division of 2 expressions, right? So you can think of this as one, the formula is one function divided by a second function. But you can also think of it as just if you have a function whose formula is one expression divided by a second expression. Now, the quotient rule is, although it is a companion of the product rule, it's harder than the product rule. All right. So this one is harder to memorize and harder to remember. And you can see it's more complicated, right? Okay. All right. So here's what the quotient rule says, right? So you have, again, this applies when you have one expression divided by a second expression. So numerator divided by denominator here, right? Okay. All right. So here's what you do to find the derivative. You take the derivative of the top, and then you multiply it by the bottom. Just keep the bottom though. All right. So don't take the derivative of the bottom. Then you don't add here, you subtract. Okay. So different from the product rule, you subtract, and then you keep the top times the derivative of the bottom. So just like in the product rule, you're alternating derivatives, right? Okay. But you subtract instead of add. And then also in the quotient rule, you have a denominator, and that denominator is going to be the original denominator squared. Okay, so you take the original denominator and you square that. That becomes the denominator of the derivative. You guys think you can remember this formula? It'll take a little bit of practice to remember it. All right, so it's very similar to the product rule, right? Derivative of top times bottom minus, you subtract instead of add, top times the derivative of the bottom, and then you square the bottom, not the derivative of the bottom, just the original bottom squared. Okay, the original denominator squared. And you come up with a pretty messy looking derivative. Now that's just life. Okay, the derivative comes out kind of messy there. Ooh, let's try one, maybe not too hard here. Well, here's the original example that we started with, I think. So suppose we have this function, h of x is 5x minus 2 over x squared plus 1. See, so there you have the quotient of two expressions, right? You have expression in the top, 5x minus 2, divided by this expression in the bottom right, x squared plus 1. All right, so according to my quotient rule, let's see, what's the derivative going to be? All right. So you're going to end up with a big fraction here. So if you want to, you can go ahead and write that down first. First, take the derivative of the top, the 5x minus 2, and then multiply that by the bottom, but not the derivative of the bottom, just the original denominator. What is the derivative of 5x minus 2? Or can y'all do that quickly? What's the derivative of 5x minus 2?
5.
Yeah, just plain 5. Yeah, great. That's just 5. See, the derivative of 5x is 5. The derivative of 2 is 0. So that's gonna that 2 is just gonna disappear. So you have 5, and then keep the denominator, keep the x squared plus 1. And then now, unlike the product rule, you're gonna subtract. All right. And now you just reverse the process. Keep the 5x minus 2, and then take the derivative of the bottom. What's the derivative of x squared plus 1?
2x.
Yeah, it's 2x. So times here, 2x. And then the denominator is kind of messy, but it's not hard to write down. You take the original denominator, the x squared plus 1, and you square that. I wrote square brackets there, but you could have put parentheses also. Okay, so you just take the original denominator and square it. There it is. There is your derivative. Now we can clean this up a little bit, I think, to make it look a little bit nicer, but that is the derivative. Let's see. So 5 times x squared plus 1, that's 5x squared plus 5. And now be careful about this minus sign. And here also you have a product. So let's see if we can do all of this. 5x times 2x is 10x squared, right? 5x times 2x is 10x squared. But don't forget it's negative. So I have minus 10x squared. And then minus 2 times 2x is minus 4x. But I have this minus. So that makes it plus 4x. And then the denominator we'll just keep that, x squared plus 1. squared. And let's see, do I have any like terms here? Yeah, a little bit. 5x squared minus 10x squared is minus 5x squared. And then you have a plus 4x, this term, and then you have a plus 5. All of that over, and we just keep that x squared plus 1 squared. That's kind of as simplified as we can make it. So you come up with an ugly derivative. It's not a very pretty derivative, but there is the derivative. So we can use that for whatever we need to use the derivative for, right? Which is things like calculating velocities or finding turning points, right? Okay. Those are the sorts of things that we've been using derivatives for. Okay. So I guess we should have expected to have kind of a messy derivative here because the original function was kind of a messy function, right? So it's not surprising that the derivative comes out looking kind of ugly too. Okay, so well, there's at least a couple of examples of the product and the quotient rule. I'm going to leave you with a problem here, and we'll take a little break here, but I'll leave you with this problem. So let's see if we can differentiate this function. H of x is 3x minus 2x squared, and then times 5 plus 4x. So that's obviously a product, right, of two expressions, right? Okay, pretty clearly. That's the product of two expressions, right? The 3x minus 2x squared and the 5 plus the 4x. So see if you can find the derivative here. Obviously, you're going to use the product rule, right? Okay, because we're differentiating a product. All right, so try working on that while we're taking a little bit of a break here, and then we'll come back and talk about that one in about 6 minutes here, right? So we'll reconvene here in at about 12:35. If I can get the camera. All right, so let's pause the recording. Okay, I'm back. Are y'all back? I've resumed the recording. So let's take a look at this. Let's take a look at this part C here and see if we can write down a formula for the derivative of this function h. It's always a question when you're using the product rule and the quotient rule at the end of the problem, when you've already computed the derivative, how much to simplify. And there's really no good answer to that question. How much to simplify? It kind of depends on what you're using the derivative for, okay? Generally, you're not just finding derivatives in order to find derivatives. You're usually finding derivatives in order to answer some other question, right? Such as a velocity question or, where turning points are located or where a function is increasing or decreasing, because those are the sorts of questions that derivatives help you answer. So it's often deciding how much to simplify the derivative depends on, again, what you need to use the derivative for. All right, but anyway, let's go ahead and start with this function h, okay? And so we already decided, right, that we were going to use the product rule here, right? So we just have to remember the product rule, and again, that's fairly simple to remember, just because of the alternating nature of the product rule, right? Which, and the product rule is, right, you take the derivative of your first factor, the first thing that you're multiplying, right? And then you multiply that by the second factor, but you don't differentiate the second factor, right? So to start this, you would keep the 5 plus the 4x, but you would have to differentiate the 3x minus 2x squared. Okay, so let's do that. So let's see if someone wrote that one down. Angel, you're well, I see your name there, so I hope you're still with us there. Do you know the derivative of 3x minus 2x squared, Angel? You can type it in if you can't say it. The derivative of 3x minus 2x squared. There we're gonna just kind of use the maybe use the power rule there a little bit, okay? But very simple version of the power rule. Angel, are you there? Are you listening to me? Are you back from the are you back from the break? No, not there. Okay. All right. So I'm just trying to get you a grade assigned there. Malcolm, are you there? So are you still there? Do you know the derivative of 3x minus 2x squared? So just this part, right? Just the 3x minus 2x squared. If you start differentiating that, Malcolm, what's the derivative of 3x? Right. Yeah. All right. So you already did it for me. So I was trying to break it up for you, but you didn't need that help. Okay. So you're right. So Malcolm says 3 minus 4x, which is perfectly correct. So we get 3 minus 4x times 5 plus 4x. All right. Plus, then you're going to switch that, right? So you're going to keep the 3x minus the 2x squared, and then take the derivative 5 plus 4x. So Malcolm, help me again. What's the derivative of 5 plus 4x? That one's pretty easy, right? What's the derivative of 5 plus 4x? 4, exactly. So there it is. Okay. It's just that easy. So there we have the entire derivative now written down. Now, again, the question at this point is, how much do we want to simplify this derivative? Let's go ahead and simplify it a little bit. So I'm going to multiply the 3 minus 4x times the 5 plus 4x. That's because that's just easy algebra. So you would have 3 times 5, that's 15. 3 times 4x is 12x. And then you would have minus 4x times 5, that's minus 20x. And then minus 4x times plus 4x, that looks like minus 16x squared. And now let's expand this set of parentheses. So I have 4 times 3x is 12x. And then 4 times minus 2x squared, that's minus 8x squared, right? And now we just add like terms together. Let's see, what like terms do I have here? I don't think there's any other constant term other than 15. So we'll keep the 15. How many x's do we have here, though? There's a plus 12x, and there's another plus 12x. So that's 24x, but then we're subtracting 20x from that. So it looks like we end up with just positive 4x there for the x terms. So those are all gone. And then you get minus 16x squared minus 8x squared, right? That's minus 24x squared. So there's our simplified version of the derivative, right? Okay. Did y'all get that right? At least the first step? Did y'all at least get started on that correct with the product rule? It looks like Malcolm did it beautifully there. Okay. All right. Let's see what other examples here I've got. Yeah, that one's kind of yucky. We'll save this one, I think, for this is well, maybe that's not. I need a better example of a quotient rule. So let me simplify this one a little bit. This one's a little bit unnecessarily difficult. So let me take this square root off, because that's going to complicate matters. All right, so let's try this one together. Let's see if we can find the derivative of this function h, okay? Which is clearly a quotient, right? Because we have x divided by x squared plus 1. And so that looks like a good opportunity there for using, the quotient rule, right? Okay, actually a perfect opportunity for using the quotient rule, if you can remember the quotient rule, right? Okay, so all right, so you guys start this one, and then we'll look at it once I give you all a chance to work on it a little bit. We'll look at it together, right? So see if you can differentiate this one using the quotient rule. So remember how the quotient rule works. It's very much like the product rule, right? Except just a little bit more. You take derivative of top times the bottom, then minus keep the top and take the derivative of the bottom, and then you divide all of that by the bottom squared, all right? So just take the bottom and square that. So see if y'all can get started or even remember the quotient rule applied to this formula. I'm only going to give you a couple of minutes because if you don't get all the way through, we'll finish it together as a class. Okay, let's come back together here really fast. So, because we need to do make a little bit more progress in the notes, but let's start writing down what the derivative of this function h will look like. And let's start with the bottom, but the denominator here, because that's the easiest part to write down first in the quotient rule. So, Saad, are you there?
Yes, Professor, I'm here.
Yeah, so what do you put in as the denominator of this derivative, Saad? What's going to
Can you hear me?
go? Yeah, I can hear you fine. So
Sir?
what are you going to put here as the derivative of the denominator? I'm sorry, the denominator of the derivative. Set it backwards. According to the quotient rule, Saad. Remember what the quotient rule says?
So first, you got to take the derivative of the the top one, which is x, and the derivative of x is 1.
Yeah.
So you
Right.
multiply that x by x squared plus 1,
Right.
and then you take the derivative of the denominator, which is 1 plus 1, so just 2x.
2x. Yeah, you're right. So the
derivative
derivative of
that
the
is
denominator
that.
is 2x, and then what?
And then you multiply that x. Multiply 2x by x.
X, right? Yeah. Now, what do you do with these two things, though?
They're multiplied together.
Not quite. Now,
Sorry,
these are
added
multiplied
together.
together.
They're
But
plus.
what?
They're added together. There's a plus sign in the middle.
Yeah. What's the sign in the middle?
Plus.
Yeah, it's minus.
Oh,
So
sorry,
that's one thing too.
minus.
That's an easy mistake to make, though. Okay, because in the product rule, they're added, but in the quotient rule, they're subtracted. Yeah.
Okay.
So
I'll
that's
remember
easy
that.
to. Yeah, and then, but what goes in the bottom here?
The bottom
Minus
is gonna be the bottom x squared plus 1 squared.
Perfect. Yeah. Oh, so you did that beautifully. Yeah. Excellent. There it is. So in a sense, that's it. Okay. You have written down the formula there for the derivative. Now we can simplify this a little bit, not a lot. 1 times x squared plus 1 is x squared plus 1. So you can just sort of drop these parentheses, right? And then minus 2x squared, right? And then you can add these two x squared terms together. So you end up with minus x squared plus 1 over x squared plus 1 quantity squared, as I guess kind of a simplified version of the answer. All right. But already this is an answer, right? This is just kind of the simplified version of that. Oh, wow, you did that very well. Okay, so that's excellent. Now let me show you here one really powerful use of the quotient rule, because I'm going to show you now how to differentiate tangent. All right, so we know the derivative of sine is cosine, and the derivative of cosine is minus the sine. All right, so we did those two. But what about the derivative of tangent, our third favorite, our third most popular trigonometric function, right? What is its derivative going to be? Well, let me show you how we can calculate that now pretty easy. Because remember, tangent of x is the same as sine of x over cosine of x, right? And when you rewrite the tangent like this, now you can find the derivative of the tangent using the quotient rule, because here you have the tangent written as a quotient. So if we apply the quotient rule, let's see, what would the quotient rule tell us? The derivative here is, well, it's going to be, y'all just told me, right? It's the derivative of the sine times the cosine, but the derivative of sine is cosine. So you have cosine of x times cosine of x, right? Derivative of sine is cosine, and then you keep the cosine and multiply. Minus, right? And then let's see, what's the second term going to be? You keep the sine, right? And then you multiply by the derivative of the cosine. So keep the top, the sine of x, and multiply by the derivative of the cosine. But that is minus sine of x, right? And don't forget, since we're using the quotient rule, you subtract here. All of this divided by, you take the denominator and you square it. So you get cosine of x squared. Well, now let's simplify this. So cosine times cosine, that's cosine squared. I'm going to put the square in the normal place there that we do for trig functions. So we have cosine squared of x, and then here's minus sine times minus sine, so that's plus, and then squared again, right? Sine squared of x over, and then cosine of x squared. Normally you would write the square here above the cosine. That's just traditional for trig functions, right? Where you put the exponent. So that is the derivative of the tangent. But now that looks kind of ugly, but we can simplify that a little bit, because what is cosine squared of x plus sine squared of x? You remember your Pythagorean identity? The famous Pythagorean identity, cosine squared of x plus sine squared of x? What does that always add up to?
1.
1. So the numerator just becomes 1. So you have 1 over cosine squared of x. But you remember what 1 over the cosine is? That's another trig function. What trig function is 1 over the cosine?
Secant.
Secant. Perfect. Well, this is 1 over cosine squared. So what you really have here is secant squared. So there it is. We can simplify all of this. The derivative of the tangent is secant squared x. So not quite as nice as sine and cosine, but not bad. Derivative of the tangent is secant squared x. There is one thing you're going to want to memorize. Okay. All right. So derivative of sine, cosine, derivative of cosine is minus sine. Derivative of tangent, now you know, is secant almost. It's secant squared x. Secant squared x.
Sorry, can I ask you a question real quick?
Mm-hmm.
Can I ask you a question about that?
Yeah.
So you went from cosine squared x plus sine squared x to 1.
To 1, yes.
Is
That's
that
called the Pythagorean identity. Yeah. Mhm.
Okay.
Right. Yeah. Always. It's related to the Pythagorean theorem.
Yeah.
It is the Pythagorean theorem in disguise, in fact. But it's in this case, it's called the Pythagorean identity. Cosine squared of x plus sine squared of x is 1 for any x. So that simplifies really nicely to just 1. Remember also the other Pythagorean identity is secant squared of x minus tangent squared of x also is equal to 1. that's also called the Pythagorean identity, but that's kind of the less famous version of the Pythagorean identity. This is the one students always remember. But we will get a chance to use this one eventually. It does come up occasionally. Okay, let's write down the other trig derivatives as well. Okay, so so we know now that for sine of x, we know that the derivative is cosine, and for cosine, we know the derivative is minus the sine. Okay, so and now we know also, we just proved that for the tangent, the derivative of the tangent is secant squared of x. For cotangent, it's going to, and you can use exactly the same process to discover this, so I'm not going to go through the process. It turns out for the cotangent, the derivative is minus cosecant squared of x. So see, it's very similar to the tangent derivative of cotangent, but it's negative cosecant squared x. For secant, yeah, do you have a question? Did I scroll too fast?
Sorry, my bad.
Yeah. So
I was hopping down the. Okay, yeah, I got it.
Yeah.
Thanks.
So the derivative of cotangent is minus cosecant squared of x. For secant, the derivative of the secant turns out to be, it's kind of nice, it's secant tangent. So derivative of the secant is secant times the tangent. So remember, in the derivative of the secant is going to repeat itself, but then you have to multiply in the tangent. And finally, the last basic trig function is cosecant, right? Well, you can imagine that derivative is going to look kind of like the secant. The derivative of the cosecant is minus cosecant cotangent. So it has a negative in it again. All the cos, all those trig functions, cosine, cosecant, right, cotangent, they end up with negatives in their derivatives. So for cosecant, it's minus cosecant times cotangent, minus cosecant x times cotangent of x. So that list, you just have to sort of memorize it. And of course, the three that are really the most used will be a sine, cosine, and tangent. So those three are especially important to remember, but you also have to remember, just memorize the derivative also of the cotangent, the derivative of the secant, and the derivative of the cosecant. So it's not something you want to be able to reproduce. You just have to memorize those, just, you know, so that you can use them from memory. So hopefully you'll have in your homework plenty of opportunities to memorize them, but you need to sort of concentrate on, I need to memorize the derivatives of the 6 trig functions. Okay. I'm going to come back to these notes a little bit next time, okay? But I want to go back and look at, I want to go now and look at some, a little bit more fun problems to finish off today. All right, so let's look at these 2 problems and see if we can make some progress with them. So it says for the following function, find the equation of the tangent line. Find the equation of the tangent line at the given input. So the given input here is going to be at x equals 1. So we want to find what is the equation for the tangent line at x equals 1. Now, so you're writing, so the basic problem here is to write down the equation for a line, right? Okay. And so we've done that problem lots of times, writing down equations for line. So you don't want to let yourself get confused by the fact that you're dealing with a tangent line here. Tangent lines are just lines. So what we're really doing is just writing down the equation for a line. And when you write down the equation for the line, what do you need to know to write down an equation for a line? What information do you need to be able to write down the equation for a line?
Point on the line.
A point on the line, that's always basic, right? You need to have a point on the line. If you don't have a point on the line, right, you're not going to have much chance of writing down the equation for the line, right? Now, this is a tangent line, correct? And it's supposed to be tangent to this curve, whatever this curve looks like. I have no idea what this curve looks like, but it's supposed to be tangent to this curve at x equals 1. So that means this tangent line is going to contain this same point that this curve does at x equals 1. So how can you find the point on the curve at x equals 1? What do you do to find the point on this curve when x is 1?
Plug in 1 to your equation.
Yeah, you plug 1 in, right? So in other words, first thing we have to do is calculate f of 1, because that will give us a point on the tangent line, right? Okay, so I want to compute f of 1. And let's see, we can probably do that without even doing much arithmetic, right? If you plug a 1 in here for x, you're going to get 1 plus 4 times 1 plus 1, right? This is 1 cubed, which is 1, plus 4 times 1, which is 4, plus another 1. So that looks like that's going to turn out to be 6, right? And then when you plug 1 into the second set of parentheses, you get 1 minus 2, which is negative 1. So it looks like f of 1 turns out to be minus 6, right? So that means the point on this curve, when x is equal to 1, that point on the curve is, if I can get my pen to write, that point on the curve is, maybe it will write down here. That point on the curve is 1 and negative 6. So that point is also on the tangent line, right? Because remember, the tangent line is supposed to just touch the curve. Probably it won't cut through the curve. It could, but usually it won't, right? But the tangent line is supposed to touch the curve right here at this point, 1 and minus 6. So there's a point on the tangent line, all right? So Donna, we're halfway there. We have the point. What other piece of information do we need to write down the equation for a line? You need a point that the line goes through. So we have such a point. And now what else do we need to know about the line? What's the other really important piece of information about the line we need to know?
Is it slope?
Sure, it's the slope, right? So once you have the point and the slope, then you're home free, right? You can write down the equation for the line. Now, how do I find the slope of this tangent line, though? Okay, so now we're back to really the most basic calculus question there is, right? What is the slope of the tangent line? The slope of the tangent line is the same as the derivative. Yeah, see, there's a phrase I keep reminding y'all I want y'all to remember, right? Slope of the tangent line is the derivative. Yeah, okay. So to find the slope of the tangent line, we have to find the derivative at 1, right? Because that's the point, right, where we want to draw the tangent line, or in this case, find the equation of the tangent line. So the slope for the tangent line is going to be the derivative f prime at 1, okay? Well, now for me to calculate f prime of 1, I need to have the derivative function. So I need to know, well, here it comes, right? So this is why this example is here. Oh, I have to find the derivative of f. And f is f here is a product, right? It's the product of these two expressions, right? X cubed plus 4x plus 1 times x minus 2, right? So I'm going to have to use the product rule here to find the formula for the derivative. Well, I think I can do that. So I think we're pretty good at that. Now let's see. First, I want to find the derivative of x cubed plus 4x plus 1. Let's see. The power rule helps me with that really fast. Because what's the derivative of x cubed?
3x squared.
Yes. And the derivative of 4x is, that's easy also,
4.
4, right. And the derivative of 1 is 0, right? Because that's a constant. Oh, so the derivative here is just 3x squared plus 4. And then remember, you keep the x minus 2. Then plus, because this is product rule, not quotient rule, so you add here, then you keep the x cubed plus 4x plus 1, and you multiply in the derivative of x minus 2. But what is the derivative of x minus 2? So what's the derivative of x minus 2? Seems too easy.
1.
1, exactly. Remember, x minus 2, if you think of that just by itself, x minus 2, if you graph that, that's going to be a straight line. So x minus 2 is going to be a straight line. And the derivatives of straight lines are just the slopes of the straight lines. The slope of x minus 2 is 1. So it has derivative 1, which is what we got there, right? So there's the formula for the derivative. Now we can simplify that if we want to by multiplying out the parentheses and adding like terms together. So we could do that, but we really don't have to go through all those steps because all I want to calculate is f prime of 1, right? I want to find what's the derivative at 1. So I can just plug 1 right into this formula, right? And let's see if we can do that arithmetic without, multiplying all of these parentheses together. Let's see, if you plug 1 in for x here, you're going to get 3 times 1 squared plus 4. I think that's 7. And then when you plug 1 in here, get 1 minus 2, which is negative 1. So you get 7 times minus 1 plus, now when I plug 1 into these parentheses, it looks like I get 1 cubed plus 4 times 1 plus 1, that's 6. 1 plus 4 plus 1 is 6, times 1. So it looks like I get minus 7 plus 6. Oh, it comes out so nice. It just turns out to be minus 1. So f prime of 1 is minus 1. So the slope of my tangent line is, at this point, at where x equals 1, the slope of that tangent line is minus 1. And we know the tangent line must go through this point because that's the point on the curve at 1. So now we write down the formula for the tangent line. Remember, it's going to be y equals the slope, which is minus 1, times x minus the x coordinate of the point you're given. So this is x minus 1. And then you just add on the y coordinate of the point that you're given, which is minus 6. So, it's just that simple. There's the equation for the tangent line.
Technically, you could write that equation in any form, right? Like if you want it to be slope intercept or something.
Yeah, you can write it. Yeah, from this point you can write it however you like it. So if you write it as if you take the parentheses off, you get y equals minus x minus a minus 1 is plus 1, and then plus 1 minus 6 is minus 5. So you could write it like this: minus x minus 5. So you would know, oh yeah, the slope is minus 1 and the y-intercept is minus 5, okay? So you could write it like this as well. But keep in mind, what we were really finding here was the equation for the line. So this was really an equation for a line problem, which just means I've got to find the slope and I've got to find the point that the line goes through. But then it turned into a calculus problem, right? Because finding the slope of this tangent line means you've got to find the derivative. So always keep that in mind. Slope of tangent line is derivative, right? Slope of tangent line is derivative, which is rate of change. Let's look at another problem like this one. And let's see if we can do this one. We have maybe just enough time to at least get started. Okay, so this says, for this function, find the points on the graph where the tangent line is horizontal. Find the points on the graph where the tangent line is horizontal. So what happens on a graph where the tangent line is horizontal? Think back to before spring break. What happens on a graph of a function where the tangent line is horizontal? What sort of thing do you get on the graph where the tangent line is horizontal?
The derivative is 0.
Well, the derivative is 0. That's correct, Donna. The derivative is going to be 0 where the tangent line is horizontal, because horizontal lines have slope 0. Yeah, so you're right. The derivative is going to be 0. We're going to use that indeed in just a second here, but let's think back a little bit more graphically. If you're thinking about the graph of this function, who knows what this looks like? Well, we're going to look at in a second, but who knows what this looks like? Where the tangent line is horizontal, what sort of things do you get on the graph? What sort of points do you get on the graph where the tangent line is horizontal? What happens to the graph where a tangent line is horizontal? See, think
Is the
about
graph not smooth?
no, we're hoping the graph is always smooth. Okay, we want the graph to be smooth because otherwise we won't be able to compute a derivative. So, you know, if we have any jagged points on the graph, there won't be a derivative sod. But think about just, I'm going to draw a graph, but it has nothing to do with this one. I'm just thinking about in general. When you draw a graph and where the tangent line is horizontal, remember what happens on the graph. Let's see, here the tangent line, right there, the tangent line is going to be horizontal, right? Right there. And right over here, right? Is the tangent line going to be horizontal over here? And what's happening on the graph where the tangent line is horizontal?
It's a turning point.
Yeah, it's a turning point, right? So really what I'm asking here is another form of where are the turning points on this function? Okay, yeah, I'm looking for the turning points, okay, where the function is switching from increasing to decreasing or vice versa. Now, I drew a really easy picture here, but that's, in general, that's not an easy question because I'm going to show you this graph. And here's this graph. Wow, it's terrible looking. You see, y'all see that? There's the graph of x minus 4 over x squared minus 7. It's broken into 3 parts. It's got 3 branches, okay? And the branches, you know, I guess they're easy graphs, but it's not at all easy to figure out where the turning points are, right? Just from looking at the graph, it looks like there's a turning point maybe right about here, because see, somewhere down here, the graph is going to bottom out, right? And it's going to switch from decreasing to increasing, but God, where is that? It's somewhere, it looks like it's somewhere between 0 and 2, but I have no idea where. Maybe about right here. Very hard to see. And it's even worse over here on the far right. See, this graph is going up and you can barely see it, but it goes up and it peaks out. So somewhere over here, it peaks out and then it starts falling back down again and gets close to the x-axis. But wow, I can't see that at all. Where is that turning point? Or is there even, maybe there's not even a turning. Okay, but in other words, is this graph coming up and coming back down? It's so close to the x-axis, I can't even see it. So so that's very difficult to find those turning points from looking at the graph, but we don't have to look at the graph right now, right? Okay, because now we have calculus, see? So this is where calculus is going to help us. So we can find those places where the tangent line is horizontal. In other words, we can find those turning points without having to eyeball it off of a graph. Very hard to find on the graph. We can do it just with pencil and paper. We can do it analytically. But we have to be able to find the what? What function do we have to be able to find the places where the tangent line is horizontal? Begins with a D.
Derivative.
Derivative, yeah. We have to be able to find the derivative. And then set the derivative function to 0 because the tangent line is going to be horizontal where the tangent line has slope 0, right? So take your derivative function, which gives you slopes of tangent lines, and set that to 0. And then you can discover, if you can solve an equation, you can discover where the tangent line is horizontal. But that means we have to be able to compute the derivative, okay? Well, we're not gonna have time to do that, but just tell me, what rule am I gonna use to find the derivative here? Of this formula? X minus 4 over x squared minus 7?
The quotient rule.
The quotient rule, exactly, Saad. We're going to use the quotient rule to find the derivative. And then once we find that derivative, we're going to set it to 0 so we can figure out where the derivative is 0. In other words, where the slope of the tangent line is 0, or in other words, where the tangent line is horizontal. So that's how we're going to find those turning points, which are very hard to see on the graph. Okay, well, we've run out of time, so we'll have to start next time with finishing this problem, right? Okay, and then a couple of other things from this note that I didn't get to go through today. All right. Well, at least you know the product rule and the quotient rule now. So when you finish that basic differentiation homework, you can start on your product and quotient rule homework, because that's just going to be practice with using the product and the quotient rule. Okay. All right. So well, we're out of time, so I'm going to stop there, and I'll see you guys on Thursday. Y'all did really well today. So it was a really great session. So thanks to everyone for answering my questions. Y'all really did that really great. So now I can make the test even harder. No, I'm just kidding. All right, I'm going to stop the recording.